Hi everyone, and welcome to this video on binomial hypothesis testing. So this is the video number 1. We're just going to look at the basics today, and it'll probably be a 3-part video series. So we're going to start off by looking at what we mean by a significant result, and this is the key to understanding this topic. So let's look at this scenario here. So imagine there's a treatment, a certain drug that's out at the moment, and someone new comes along and says, I've got a better treatment. And you know, this could be just as effective or more effective. It could be cheaper, for example. And so if it's cheaper and more effective, of course we'd want to switch. But we just don't take the person's word that's selling it, because obviously they're going to say that, right? So we have to do a test. So we have a certain number of people, we treat them, and we see if it heals more people or it's more effective. And what we have to do is think of a cutoff, like when are we going to say it's more effective or not? What is the probability of a certain result happening? So what we do say is if a result has a less than a 5% chance of happening, that's pretty rare. Think about it like someone at the crossbar challenge. This is an easy example for everyone to understand. So hitting a ball on the crossbar is a particularly difficult skill. If someone says I am much better, you know, when would you be impressed how many times they can hit the crossbar? Or if they hit it 3 times in a row, you'd say that's really, really unlikely. Maybe the chance of that happening is less than 5%. So that would be quite a special occasion, a rare moment. So if a treatment treats a certain amount of people and we deem that to be less than a 5% chance of happening, that's a rare moment, and we should think about making changes or a switch to this new treatment. Okay, so when we talk about things being significant, it's less than a 5% chance of happening. That means it's rare. It hasn't happened before, and it's not just down to probability. So let's have a look at this scenario here. So we have a dice. It's a 6-sided dice, a normal dice. We're going to throw it 30 times, and we're looking at the number of times a 6 appears. So let's just start by defining our random variable. So x is our random variable, number of 6s. I'm just going to shorten it as much as I can. So we could specify a model that the number of 6s appearing is distributed binomially. We're going to do 30 rolls. And what you'll notice is sometimes they'll put a p here instead of what you'd expect them to put as 1/6. Because at this moment we don't know whether the dice is fair, because it doesn't tell us, or that it's biased. So when you see something like this, this is you need to realize basically this is now talking about a hypothesis test. And a hypothesis is like an idea that we're going to test. So we have what's called a null hypothesis, H0, 0 for null. And that's always going to be, in this case, probability is 1/6. It's going to assume that the dice is not biased. It's the probability of this event that we would expect. So obviously it's not going to be a 6th if you're not talking about dice, but it's the probability that you expect it to be. Then there's going to be a alternative hypothesis we call H1, and that could be a range of things. That could be, well, it's not a 6th, it's less than a 6th. It could be, well, I expect the probability to be more than a 6. So, for example, let's say we only got 0 rolls. We would expect a lot. Well, we'd expect 5, right? So maybe we'd go for that if it was 0. If we had 12, well, maybe it's that. If we're unsure, but we just want to test it to see if it is biased or not, we could even say it's this. It's not a 6th, and you could investigate either end. So, if we were to draw a diagram of what's actually happening. There's 0 to 30, so we could get 0 6s, or we could get all of them being 6s, but we'd expect, and we use a capital E for expect, we expect our observed value to be around 5. So if you're looking at this, it could be just in this tail. If it was here, you'd be looking at this tail, and if it was not equal to 6, you'd investigate both tails. So you notice I've introduced a new word there, is tails. If it was the red or the green, we call those one-tail tests. We're looking at the lower tail or the upper tail. And if it's a two-tailed test, it would be this one here when we're unsure what the probability is, so we investigate the lower and the upper tail. So let's have a look in a little bit more detail on these one-tail tests. So just to reiterate, if we're going to use our our alternative hypothesis to be less than a sixth, we are only looking in this tail. So then what we'd say is we would reject H0. And remember, the whole point is we're looking if this dice is a normal dice, that the probability is a sixth, or we're looking now, maybe there's something wrong with this dice. Maybe it's biased, maybe it's just faulty, and the probability is less than the sixth. So we will reject H0 and say there's something wrong with this dice, if and only if the probability of the number of sixes rolled is less than a certain number. So that could be 0, it could be 1, it could be 2. Given that x is distributed binomially, we'll have 30 rolls and the probability is a sixth. But we're only going to reject it if the chance of this happening is less than 0.05, or it could be less than 0.01, or sometimes you'll see 0.1. These are called significance levels, often used the symbol alpha. And significance levels are normally 5%, 1%, or on a rare occasion 10%. Remember what I said earlier. We're only going to reject things if they're rare, they're really unlikely to happen, so it's a pretty special moment in time. And we're only going to say it's a pretty special moment in time if it's less than 5% or 1%, or sometimes less than 10%. Now, if you look at this diagram, we're not too sure where this value is, and that's what we're going to be testing for. So if you look at this situation here, this could have anything in here could be, that could happen through chance, that could be probability. Maybe 0 is the only significant result. Maybe 1 is. Say there's a 1 here, maybe that's really rare. Or how far does this box shift up? That's what we're investigating. When is a result rare or unrare? Okay, so for a lower tail test, it's going to look something like this when we set it up, and then we use our calculators or the tables to answer it. Now, if we go to the upper tail, so we're now looking at this region, we're going to reject H0 if and only if the probability that the number of sixes appearing is greater than or equal to this certain result. Remember, if this is probability, this is this certain result here. This is what we're talking about. We just don't know where it is yet. And then we specify the model. This is a really good habit to get into. If you forget to specify the model early on, you can get some marks here. And again, we're only going to say the probability is more than a sixth if and only if the number it gets along this number line up here is really rare, it's significant, and again, it could be less than 5%, less than 1%. It can be any percentage, whatever the question specifies, but these are the most two common ones. Okay. If it was a two-tailed test, and again, there's a region of probability, but do we get a significant result down here? We're not too sure whether we're going to say the probability is lower or higher. It's just different. We would be looking at a two-tailed test. Now, something weird happens here that you have to remember is if we ask you to test to 5%, what you need to remember is on a two-tailed test, you can see it easy from this symbol here because it's telling you to go into the lower tail and the upper tail. We actually split the significance level in two. We just divide it up into the two tails. The only thing that will change is here, for example, this would be now 2.5%, and this one would be 2.5%, and you just do both of them at the same time. Okay, so if it's a one tail, we just do one. If it's lower or upper, if it's a two tail, we actually have to do both. So it's a little bit more work with the two tail. I think at this moment you're probably like, what is it going on about? So let's have a look at some questions and it becomes a lot more simple. So here we have a six-sided dice. You'll notice it doesn't say whether it's fair or it's biased. We're going to go on to something a little bit more interesting than dice. We have a result this time. So we have only 1 6 appears after 24 rolls. Now, it's telling us to do a one-tailed test. Normally there's a little bit of language to say, we'd expect a lower probability or upper, or the probability is different. the language kind of gives it away, whether it's a one-tail or two-tail test. In this video, we're only going to look at one-tail tests, but this question could very easily lend itself to two-tail. And we're going to decide whether it is biased or not. You'll notice it hasn't told us which tail to use, but it's pretty obvious using this result. Okay, so let's have a look at this. Let's just try and draw a picture. So we could have no sixes. We could have 24 sixes, but how many would we expect from a fair dice? Well, a sixth of the time we'd expect a 6. So a sixth of 24 is 4. So what we haven't done is haven't defined the variable, so I'm just going to do that very quickly. It's the same as the last one, so it feels a bit of a painful to do this, but we'll just do it quickly. So number of sixes appeared. So x is distributed binomially. This time we have 24 rows, and we're investigating a hypothesis test, so we're just going to put the p in there. Okay, so what are our hypotheses? So remember the first one, the null hypothesis, H0, is going to be what we assume it is, like if it's fair. H1, now what are they asking us to do? So because we have an observed value, so this our x is 1, you'll see this is below what we'd expect. So there's no point investigating the upper tail, especially when it tells us to do a one tail. So we are doing a lower tail test. So that means we're going to investigate lower than 1/6. So we will reject H0. We will say that this dice is biased if and only if the probability that the number of sixes appeared, the probability of this happening is, so what is the probability of getting 1 or less sixes? Given that, we're going to look at the model of it being 30 and a sixth. We can't use our tables for a sixth. We can for 30, but the probability means we're going to have to use our calculators. And you see the significance level here in bold is 5%. So we're going to only reject it if the chance of that happening is lower than 5%. So bear with me. I'm just going to grab my calculator as well. You can do it with me. So we're going to go to the distribution. We're looking at more than 1 point, so we're looking at cumulatives of 0 plus 1, so it's the binomial CD. We want to use the variable option because we're not producing a list of numbers, and our x is 1. Our n is, oh, sorry, that's wrong, that's from the previous question, that should be 24, please excuse me, so that's 24, and the probability is 1 divided by 6. So that gives me a result of, oh, James Bond, 0.0729, and I'm going to write that. Okay, so what is that percentage? That is 7.296. So what we're saying is there was a 7.296% chance of only getting 1/6 from 24 results. So what we're actually going to say is that is in that area of probability. We're only, remember, going to reject H0 if it was lower than a 5% chance of happening. So we are accepting H0. So therefore, we accept H0 and we write something like this. So we say insufficient evidence. So always important to write a conclusion. So insufficient evidence to suggest the dice is biased. And that's it. That's a one-tail test. My setup, you won't see it everywhere. I think it's really clear. You can skip a lot of it, but I just think if you want a really solid understanding, this is a good method to follow. Let's have a look at another question. This is a little bit more interesting from a business point of view. So we have Luigi. In his restaurant, he knows 1 in 10 people order a Pinot Grigio. That's a white wine. That's from previous orders. So he knows that a certain number of Pinot Grigios he orders every week, so he doesn't want to run out. It's time to do a new sample. So he takes a sample of 50 and he has a result of 11. And he wants to know whether the drink has become more popular. So there are obviously trends that happen all the time, and if you're only in a restaurant, you don't want to miss out on these trends. So he wants to know, very simply, is it more popular? He's only going to make changes if the chance or the result of this happening is significant. and he's going to look at the significance level of being 1%, so really, really rare. Okay, so let's define our random variable. I'm going to stick with x's, so the number of Pinot Grigios ordered We're going to define our parameters, so n is 50, and we're just going to put a p here because we're testing the probability. We're seeing if it's what we expect or if it's lower or higher. So h0, the probability is what we're expecting. So we're expecting it to still be 1 in 10, so 1 out of 10. Before I do my null hypothesis, I do like to draw a drawing. So we've got no people could order a Pinot Grigio, or it could be 50. We would expect a tenth of that, so we would expect 5. So where is significant? Now, he's expecting it to become more popular. Can you see this language? He's expecting the probability to be greater than 1 in 10. So from the language, we're looking at something greater than a tenth. You could say the 11 tells us this. This is our observed value. This is 11. But you can't decide whether it's a one-tailed test or a two-tailed test just from the observed value. You could still be doing a two-tailed, but it's this language here. If he said he expects the drink or the probability to be different, that's the hint towards a two-tailed test. Okay, so we are doing an upper tail test, which is slightly more work, but it's no problem. So we're going to reject h0 if and only if the probability that the number of Pinot Grigios being greater or being ordered is greater than 11. 11, let's do greater than or equal to 11 because there was 11 ordered. So the number of Pinot Grigios ordered is distributed binomially with 50, and we're going to now put the probability in because this is the parameters that we're testing. But we're only going to reject it if the chance of 11 being ordered is so rare, so significant, it's only a 1% chance of happening. Now, just to remind you, how do we solve this? Well, this is the same as 1 minus up to and including 10. So let's work out what up to including 10 is. So we're going to put x in as 10, 50 is our n. We could use the tables for this. I've got my calculator. And that's 0.1. So I've got here is 0.9906. So take this away from 1, and remember, you can just make these all 9. So that's already a 9. So 0, already a 9, 0, make that a 9, and the last one 10. So this actually has a 0.94% chance of happening. So what are we going to do? We're going to reject it. We said we reject h0 if it was a lower than 1%. So we're rejecting h0. We're saying that's not happening. We're saying that this one is true. So we're going to write that down as reject h0. And what does that mean to Luigi? So there's evidence to suggest Pinot Grigio is more popular. So what would that mean for him? He should order more. Okay, he doesn't want to run out. They might go to a different restaurant next door if they haven't got the wine that everyone wants to drink. Okay, so hopefully you can see from a business point of view, this is quite an important topic. So do spend some time on it and practice. Any questions, please leave a comment in the comment section. Okay, cheerio everyone, good luck, bye.